Hi, my name is Mahsa Orvani. In this video, I will present GKD semi-supervised graph knowledge distillation for graph-independent inference. Graphs are successful in modeling and analyzing multimodal medical datasets. One or more modalities form the graph between patients, and the rest of the modalities remain as patient features. Now the disease prediction problem will turn into the node classification problem. Meanwhile, graph neural networks provide deep learning architectures for integrating information of graph topology and node features to extract more meaningful embedding for disease prediction tasks. In this paper, we focus on the semi-supervised and inductive setting, where part of the training samples are unlabeled and the test samples are not seen by the model during the training. Every layer of a GNN has two steps. First, smoothing each node's features by aggregating with its neighbors, and then use those new features as input to a fully connected layer. This aggregation step changes the input space by reducing the variance of the input features. In this graph, assume that color shows the node features. Two nodes with the same color will end up in totally two different colors after two steps of aggregation, because one of them is filtered by its neighbors, but the other one is isolated. This problem gets more serious when the graph is available during training, but missing at the test time, and all the test samples are isolated nodes. Therefore, the feature space of training and test samples are different. GKD is our method, which aims at using labeled and unlabeled training samples and the graph between them to train a model with input feature space without filtering by neighbors, and use the train model for isolated nodes at inference time. GKD has two blocks. The first one is called teacher. This teacher will extract and learn all the information from the labeled and unlabeled training samples and the graph between them. The goal of this block is to summarize all the available data and use them to provide pseudo-self labels for unlabeled training samples. In this step, it doesn't matter for the teacher to be trained in the input or filtered feature space. The second block is the student network. Now where the teacher has distilled all available information into training data and provided pseudo-self labels, we will transfer this knowledge to the student network. The goal of the student network is to imitate the teacher as a rich model, so the output of the teacher will be used to train the student. The important part is that the unfiltered input features are used as input to the student network to force its parameters to be trained in this feature space and make it functional to the test set without the graph. Now we will see that how our proposed teacher block works in details. In the teacher block, we first train a fully connected network with labeled training samples. In the next step, we use the train network to assign pseudo-self labels to unlabeled training samples. Then the graph comes in. We smooth the labels of each node with its neighbors through our modified label propagation algorithm. In the basic algorithm, only training samples propagate their labels. But in our proposed teacher, all samples communicate and update the other labels through the graph. In addition to that, we modify the algorithm by using a weighted sum between the output of the label propagation and the primary labels comes from the fully connected network in the previous step. So we have a balance between the graph and the features to reach our goal of knowledge distillation in this block. This is the complete overview of our GKD model. As we said before, the train teacher block obtains all the knowledge from the graph and features and then summarizes it in the filtered labels. Then this knowledge will be transferred to the student network through a cross-entropy loss between the student output and the filtered labels from teacher. We evaluated GKD on two real datasets and compared with graph and non-graph based state-of-the-art methods. This figure shows the performance of methods on a byte dataset. GKD is shown in red. It should be noted that GKD without modification in label propagation is also shown with cyan color. In prediction of autism on a byte dataset, GKD shows superior and more stable results than its competitors. Similar results are obtained for predicting the progress in Alzheimer's disease on tadpole datasets. Especially GKD has improvement in macroflon, which is an important measurement in our tadpole dataset with imbalanced classes. In this video, we talked about our proposed method for disease prediction problem in graph-based dataset with semi-supervised inductive setting, which is not relied on the availability of graph at inference time. Please check our paper for more results and a deeper understanding of method. Thank you for your attention.